Hi, I am Shahnawaz. In last lecture, we studied the freeness property of free abelian groups. That is, we studied that if suppose we have a free abelian group, say F, with basis say x is equal to x1 through xn. So we have a map here from x to F by the inclusion. So this is the inclusion map because these elements in X they also lie in the field in the free abelian group F. So the freeness property is that suppose we have any abelian group G and a map from the basis set X to G. See, this is the map phi. Then by freeness property we mean that we can lift this map from the basis set of F to G to a unique homomorphism, say gamma, say gamma. So we can lift this map from this basis set to the unique isomorphism gamma from F to G. That is called the freeness property of free abelian groups. Now it is natural to ask whether the converse of this freeness property is true or not. That is, suppose we have any abelian group F here and a list of elements, say x1, x2, xn. So right now this is just a list of elements in X. So if this F has freeness property, that it means if any map say gamma from X to G can be lifted to a unique homomorphism phi from F to G, then it is natural to ask whether F is free or not. Well, the answer is yes, and we are going to prove the following result for the answer. So we have the following proposition. Say let x is equal to x1 so on xn be a set of elements, be a set of elements in an abelian group. F, and we are assuming that this F has a freeness property, and let F have F has the freeness property that is by freeness property we mean that is for every abelian group G and every function say gamma from X to G, there exists a unique homomorphism. There exists a unique homomorphism say phi from F to G with phi of xi same as gamma of xi for all I. Then F is a free abelian group of rank R and basis X. Then F is a free abelian group of rank N and basis X. Let us prove this result here. So we have X, a subset of X. So X is given to be a subset of X. So a subset of F. So we have the natural inclusion map. Let us know that map by I. Let I from X to F be the inclusion. So this is the inclusion map. Be the inclusion. Let us consider a basis of z to the power n. I mean the n copies of z. Let e1 so on en be a basis of free abelian group z to the n. Notice that each ei is an n tuple where there is exactly one non-zero component at the ith position, which is 1, and all other components are 0. So Zn is given to be a free abelian group. So let us take this basis to be equal to y. So if y is basis of z power n, so there is also a natural inclusion map from y to z power n, because each ei is in Zn. And let us note this inclusion by j. Let j from say from y to z power n be the inclusion map. Let us keep this in mind. Each free abelian group has freeness property. Now what we are doing here, we are proving that if a free abelian group has the freeness property, then it has to be a free abelian group. So let us define a map. So we are going to define a map from x to y and y to x. So define say p from x to y as, so p takes an element of x, say xi, to an element of y, say ei, and define another map in the reverse direction, that is from y to x, as naturally, that is q takes the element ei to the element xi of x. So this is true for all x. Now it is given that f has freeness property for any abelian group G. So if f has freeness property for any abelian group G, in particular it has the freeness property for z to the power n as well. by freeness property of f. So let us understand this here. So we have x here. Now this x is embedded in f. So this is z to the power n. So as such we don't have a map direct map from x to the power n. However, we have a map x from x to y, which is this map p, and from y to z we have the map which is an inclusion map j. So this composition map j composed with p is a map from x to y. So this is j composed with p. So since f has the freeness property for any abelian group, g in particular it has the freeness property for z power n. So this map can be lifted to a unique homomorphism, say phi from f to z power n. So what we have to do, we have to prove f is a free abelian group. In particular, we have to prove f is isomorphic to z power n. So since this phi is homomorphism, so we have proved that f is homomorphic to z power n. Now it remains to prove that phi is bijective, i.e. it is injective as well as surjective. So we are halfway done. So by freeness property of f, there exists a unique homomorphism, that is this homomorphism phi from f to z power n, a unique homomorphism. So this is the inclusion map here, a unique homomorphism phi from f to z power n, such that, so there are two ways to go from x to z power n. That is, first go from x to z power n by this map j composed with p, or first go from x to f by this inclusion map I, and then follow phi. So such that this composition phi composed with I is this map j composed with p. So this follows by the freeness property of f. But note that z to the power n is also free. So if z power n is free group, so it has freeness property also. Now z power n being free abelian group, with a basis y, then it has the freeness property. So we have from the diagram suppose this diagram is here, it is given to be here. So so we have y here. Now from y to z power n we have this inclusion map z power n. Now this z power n is free group, so it has a freeness property. That is, if we have any abelian group G here and a map from this basis set to G, then this map can be lifted from z power. So if G is here, so we can lift this gamma to this unique homomorphism phi from z power n to G. So if we in place of G we take Z F. Now F is given to be an abelian group, so we can replace G by F. So in particular this Z power n has freeness property for F as well, so we can replace here G with F here. Now we don't have a direct map from Y to F, but we have a map from Y to X, which is a map Q, and from X to F we have the map I. So this gamma is nothing but this is the map I composed with Q. So this map can be lifted to a unique homomorphism, say psi, from Z power n to F. So we have from the diagram which is given below, we have from this diagram. So from this diagram, this map is just this map psi composed with I. So from the diagram given below we have a unique homomorphism psi from Z power n to F such that psi composed with J is I composed with Q. So this is true for any group here, any abelian group here. So we can replace F with Z power n as well. So now consider the diagram. So let us consider this diagram. So we have consider the diagram. So this is X here, this is F here, this is F here, so this is I and this is I. Now note that we have this phi from F to Z power n. So this phi is from F to Zn here, and this psi is from Zn to F. Psi is from Zn to this F. So this psi composed with phi is a map from, now phi is homomorphism, psi is homomorphism, so this composition is also a homomorphism. So this is a map from phi F to F. So this is psi of phi. Note that this F has freeness property. So this means that this psi of phi is, so we can write over here, consider the diagram this. Note that psi of phi, say let us map this to say suppose some x. Now this psi phi is same as this psi phi, this. So if let us operate this on this let us compose these three maps: psi composite with phi and composite with I. So this psi phi of I, it has to be equal to I here. So we had to prove this. So if psi composite with phi is this I, then this means, so if we prove this I is limited to this homomorphism here, that means this has occurred here due to the freeness property of F. So if we prove this composition is I, then we are done here. So psi phi of I is same as psi of phi composite with I. Now phi I is same as here J composite with P. So this is psi, this is J composite with P. Now this is psi composite J composite with P. Now J composite with P is same as psi composite with J. Psi composite with J is same as I composite with Q. So this is same as I composite with Q. This is composition P here. Now this is I composite with P, Q composite P. Q composite P. One can note at the beginning of this lecture, P composite with Q is identity on Y, and Q composite with P is identity on X. So Q composite with P is just identity on X. So that is just I here. So this means this psi of phi is due to the freeness property of F. But this psi of phi being the unique such homomorphism, one can note that we have also a homomorphism from F to F given by the identity homomorphism. So uniqueness hypothesis, uniqueness hypothesis shows that psi composite with phi is the unique such homomorphism from F to F. But from F to F we have also the identity homomorphism, but ID on F, which is the identity homomorphism on F, is another such homomorphism. Therefore this psi composite with phi is just the identity homomorphism of F. Now if this is identity homomorphism, this implies psi is injective and phi is surjective. Now what we have to show? We have to show F is free. So if we show F is isomorphic to Z power n, then we are done. Now between F and Z n there is a homomorphism phi. Now we have to phi is given to be here a homomorphism which occurs here due to the freeness property of F. Now what we have to prove? We have to just prove phi is bijective, that is, it is injective as well as surjective. Now this condition here, it shows that phi is surjective. Now it remains to prove that phi is injective. Now to prove phi is injective, we will prove that phi composite with psi is the identity map on Z power n. So in that case, psi will be injective, phi will be, sorry, psi will be surjective, phi will be injective. So we are done. Also, so to prove this phi is injective, we have to reverse the roles of f and z power n. So also we have to switch the roles of z power n and f. Also consider the diagram. So here we took this commutative diagram, and here we have f and f. So now what we will do, we will take z power n, z power n. So consider the diagram. So here we have y, this is z power n, this is z power n. So this is the inclusion j, this is the inclusion j. Now between, so we have psi from z power n to f, which is given here. This psi is from z power n to f, and this phi is from f to z power n. So phi is from f to z power n. So this composition phi composite with psi, this is from z power n to z power n. So there is a map phi composite with psi from z power n to z power n. Now we'll prove that this phi composite with psi, this shows up here due to the freeness property of f. For that we have to show this phi composite with psi composite with j is just j. Now phi composite with psi composite with j, we have to show this is this map from y to j. So this map is just this map. So this is called phi composite with psi composite j. Now psi composite j is given here. Psi composite j is I composite q. So this is phi composite I composite q. So this is phi composite with I composite with q. Now phi composite with I is given to be equal to phi composite with I, that is j composite with p, that is j composite with p. This is composition q. This is j composite with p composite with q, but p composition q is just the identity map on y. So this is j here, this is j here. So again we are going to use hypothesis by, so this is the homomorphism from z power n to z power n, which shows up here due to the freeness property of z power n. But by freeness property of z power n, there is also an identity homomorphism between z power n and the z power n. So by hypothesis, phi composite with psi from z power n to z power n is unique such homomorphism, is unique such homomorphism. But the identity on z power n is another such homomorphism. Therefore this phi composite with psi is the identity on z power n. So this implies here phi is injective. Here this shows here phi is surjective. So phi is bijective. Now what is phi? Phi is a homomorphism between f and z power n. So phi is uh, therefore phi from f to z power n is an isomorphism. Hence f is isomorphic to z power n. Now z power n being a free abelian group, this implies f is free abelian group. So if an abelian group f is such that it has freeness property for every abelian group G, then this f is a free abelian group of rank R and basis x. Now f being free with x as generating set, so x will be a basis. Now x contains n elements, so the rank of f will be n.